Hey guys, welcome back to chapter 12. In the last and most tedious of math, we are going to work a problem where we calculate this standard Gibbs Free Energy, but instead of doing it from values of standard Gibbs Free Energy of formation, we're going to do it with standard values for enthalpy, standard values for entropy, and then put it into this equation. So this is tedious in that we have to calculate enthalpy, we have to calculate entropy, and then we plug it into this equation. All right, here's the problem that we are going to work on. So calculate Gibbs free energy of this reaction at 25 degrees Celsius. Determine whether the reaction is spontaneous or not. The reaction that we're going to be looking at is sulfur dioxide reacts with half of a mole of oxygen to produce sulfur trioxide. Okay. So plan of attack, we are going to use this table of standards to calculate enthalpy. Then we're going to use this table of standards to calculate entropy. Then we are going to plug those values into this equation. When we do enthalpy, we're doing it products minus reactants. When we do entropy, we're doing products minus reactants. So it's a bit tedious, but we can do it. So let's get started. We are going to start with enthalpy. So to calculate, I love color coding things. To calculate the enthalpy of the reaction, we are going to have to calculate the enthalpy of the products minus the standard enthalpy of the reactants. So I'm going to start with the products. So products are just sulfur trioxide. So the enthalpy change for sulfur trioxide is down here. That is negative 395.7 kilojoules per mole. And then we need to take into account how many moles we're making, and in this case we're making 1 mole. Then we are going to subtract that from the enthalpy change of our reactant. So I'm going to change colors here just so you know I'm dealing with reactants now. So our reactants are going to be sulfur dioxide. So the enthalpy change for sulfur dioxide is negative 296.8 kilojoules per mole. And then we need to take into account that we're using 1 mole. And then we're going to add that to our other reactant, which is oxygen. But the enthalpy change for that is 0 because it's an elemental form, right? So just for completeness sake, 0 kilojoules per mole, and we're making a half a mole. So to clean this up, this kind of cancels out. We're just going to take these two values subtracted from one another. So moles cancel, and so essentially we are left with negative 395.7 kilojoules minus negative 296.8 kilojoules. So the enthalpy change for this reaction is negative 398.7 minus negative 296.8. And we get a value of negative 98.9 kilojoules. So that's step 1, determining the enthalpy change. Now I'm going to go to a new slide. I'm going to do the same thing for the entropy. If you would like to challenge yourself, go ahead and pause the video and see if you can determine the entropy change. Right, so I'm going to start with the entropy change for the products. So my products are sulfur trioxide. The entropy change is 256.8 joules per mole Kelvin. So we've got 256.8 joules per mole Kelvin. Then we need to acknowledge how many moles we're making, and that's 1 mole. Then we are going to add that, subtract that, products minus reactants. We're going to subtract that from the reactant side. So my reactants are going to be sulfur dioxide first. So that's 248.2. joules per mole Kelvin, and then I'm going to multiply that by 1 mole because that's how many we're using. Now we're going to add that to the other reactant, which is oxygen. So that has an entropy of 205.2 joules per mole Kelvin, and we're making using half a mole, or you could use 0.5 either way. Okay, so to clean this up, my subtraction sign got lost. I'm going to go ahead and clean up the product side. So 256.8 times 1, our moles cancel, and we're left with 256.8 joules over Kelvin. And then we're going to subtract that, products minus reactants. We're going to subtract that from the reactant side, but we got some cleaning up to do over here. So 248.2 times 1, our moles cancel. We're left with just 248.2. To this value over here, so we've got 205.2 times 0.5, or times a half. So this value becomes 102.6. Moles cancel, we're left with joules over Kelvin. And now I'm going to add those two values together. So 248.2 plus 102.6 equals, so the reactant side of this is 350.8, and that is joules over Kelvin. So to get the entropy change for this reaction, we're going to take products minus reactants, so 256.8 minus 350.8, and we get a negative 94 joules over Kelvin. The last thing that we need to do is determine the Gibbs free energy change for this reaction. And we're going to do that by taking the enthalpy minus temperature times the entropy values. Enthalpy we calculated 2 slides ago, and that was negative 98.9 kilojoules. Temperature, so we'll have to go back and read the problem for this one. But temperature, calculate Gibbs free energy at 25 degrees Celsius. So temperature right now is 25 degrees Celsius. And then the entropy change is what we just calculated, and that was negative 94 joules over Kelvin. All right, we've got a table full of results, but none of the units match. So first, I need to change this temperature into Kelvin. So just remember, temperature Kelvin is temperature Celsius plus 273. So this is going to be 25 plus 273. So this becomes 298 Kelvin. The other change that we need to make is with the joules and kilojoules. So again, I don't care which way you go. I'll accept both. But I tend to take joules to kilojoules. I just like decimals better than I like 10,000. So I'm going to divide this number by 1,000. And it's going to become negative 0.094 kilojoules over Kelvin. Now we're finally ready to plug this into our equation. So we've got negative 98.9 kilojoules minus 298 Kelvin times negative 0.094 kilojoules over Kelvin. Cleaning this up, so I'm just going to bring this down. We're at 298 Kelvin times 0.094. Kelvin on top, Kelvin on bottom. Those cancel. And we're left with just kilojoules, which is good because we're subtracting that from kilojoules. So we've got 298 times negative 0.094. So this is negative 28.0 kilojoules. And then lastly, we are going to subtract these two numbers. Negative 98.9 minus negative 28.0. And we get a Gibbs Free Energy value of negative 70.9 kilojoules. Now, we've got to think about what we just calculated, okay? Gibbs Free Energy. So that is a measurement of energy. So our units are in kilojoules. That makes sense to me, okay? So I followed my units in. I got kilojoules as my answer, and it's an energy measurement. That makes sense to me, so that's good. Lastly, the question asked, is this spontaneous or non-spontaneous? So at this point, we need to determine if that Gibbs free energy being negative is spontaneous or non-spontaneous. And a negative Gibbs free energy means that it is spontaneous. So to completely answer the question, we would say the standard Gibbs free energy of this reaction is negative 70.9 kilojoules, and that is a spontaneous reaction. That's it for videos from chapter 12. I hope you guys found these helpful.